Okay, so this is the equation for gravitational potential around a planet or a star, some object. What would it look like if I plot this as a graph? So here I have gravitational potential, capital V, on the y-axis, and you can see that's in the negative quadrant because we're going to get a negative potential. And then on the x-axis, I have the distance from the center, r. And here I've actually given that in the multiples of the radius of the planet, in this case, the Earth. So capital R is the radius of the Earth, and 2r would mean the distance from the center is twice the radius of the Earth. And if I plot this as a graph, I get an equation, a line that looks like this. This is a reciprocal line or an inverse proportionality line. And if it doesn't touch the x or y axis, so for example, if I continued, it would never actually touch the x-axis like this. Same with the y-axis. Okay, so if I want to check this on the surface, I get a gravitational potential around minus 63 megajoules per kilogram. And if I move away from it, the gravitational potential increases, it becomes less negative. So over here, for example, 2r, we expect, because of the inverse proportionality, the gravitational potential to be half. And we do get roughly minus 32 megajoules per kilogram. And if you times the distance from the center by 3, you expect a third, and then you get around minus 21, and so on. In this question, we have the graph shows how the gravitational potential around a planet varies with distance from the center. Calculate the mass of the planet. Okay, we can just use this equation here, and we can make m the subject, which gives us this equation over here. I need a set of data. I can pick any point. So I'll take from the surface. So I'll go from the surface and I'll use the potential there, which is V minus 4 times 10 to the 7. So don't forget the power that's written on the axis there. And the radius at this point is around 0.8 times 10 to the 7 meters. Okay, and then divide that by the gravitational constant, and I get a mass for the planet of 4.8 times 10 to 24 kilograms, which makes sense. Just going to be quite a large mass. And I can, to be honest, I could do this method with any point. For example, I can use this point. And if I repeat this method using the gravitational potential at that point, which is around minus 1.1 times 10 to the 7, and I multiply by the radius at that point, and then divide it by the gravitational constant there, I get roughly the same mass. Part B of the example, calculate the work done against gravity to move a 900 kilogram space probe from 2 times 10 to the 7 meters to 4 times 10 to the 7 meters. So at 2 times 10 to the 7 meters, the gravitational potential is this much here. And at 4, we can also figure that out using the graph. Okay, so if we're moving from one of those points to another, we need to figure out the change in potential. So the change in potential, just subtract the numbers like this, and we get a change in potential of 0.8 times 10 to the 7 joules per kilogram. So that is the work done per unit mass to move between those 2 points. But we're not doing per unit mass, we're moving a 900 kilogram object. So we're going to have to multiply by the mass of the object, give the change in gravitational potential energy. Now, because we're moving further away from the planet here, from the surface of the planet, we have to do work in order to move away. So the gravitational potential energy will increase in this case. Obviously, if we went from 4 times 10 to the 7 to 2 times 10 to the 7, then in that case, the gravitational potential energy would decrease by the same amount. Part C, calculate the escape velocity from the surface of the planet. On the surface of the planet, the gravitational potential is minus 4 times 10 to the 7 joules per kilogram. And if I want to escape from the surface of the planet, I need to go all the way to r equals infinity, basically very far away. And at that point, the gravitational potential is defined as 0. So the difference between 4 times 10 to the 7 joules per kilogram on the surface and infinitely far away where it's 0 is 4 times 10 to the 7 joules per kilogram. I need to multiply this by an m in order to get change in gravitational potential energy in joules. Okay, so I don't have the mass of the object, so I'm just going to use m on either side, and I'm going to see hopefully it cancels out. And how am I giving this this energy is in the form of kinetic energy. So I'm going to fire it away from the surface of the planet. So I need to give it some minimum kinetic energy, where v escape is this escape velocity. So I'm going to rearrange this. So I'm going to times both sides, cancel out the m's first, which is convenient, and then times it by 2, and then square root to get the escape velocity, which gives me around 8,900 meters per second. Part D, calculate the gravitational field strength at 2 times 10 to the 7 meters from the center. Now, there's multiple ways of doing this. One way would be to just use the equation for gravitational field strength. I have the mass of the planet because I calculated that in part A, and then the radius or the distance, I'm trying to find it as 2 times 10⁷, so I have that as well, and use this as a constant. So this will allow me to calculate the gravitational field strength. Another way is to use the gravitational potential equation. Now, if you look at this equation, if you divide both sides by r, you see you get v over r and gm over r squared. And gm over r squared, that is gravitational field strength. So to calculate that, I just had to find v over r at the point that I'm interested in. So v, which is the gravitational potential, is minus 1.6 times 10⁷ at this point, and the radius, the distance from the center at that point is 2 times 10⁷. So if I divide those two numbers, I get a gravitational field strength of 0.8 newtons per kilogram. There is another method for finding gravitational field strength, and it's to use this equation here, where G is the gravitational field strength at some point, and delta V is the change in potential around that point, and over the distance, the change in distance over that point in meters there. Okay, so this can be interpreted as gravitational field strength equals negative of the potential gradient. So by potential gradient, I mean how much the potential changes over a certain distance. So you can see here, closer to the planet, the potential is changing by 10 megajoules per kilogram, but over a smaller distance. So basically that shows that the closer the potentials are, the stronger the field is. Okay. For example, if I want to find the gravitational field strength at x, I'd do the change in potential, which is 10 megajoules per kilogram, divided by the distance between those points. So as an example, it's at that point, it would be around 1.7 newtons per kilogram. So I've divided the change in potential by the change in distance between those 2 points. If I want to find the gravitational field strength at y, I would do the same thing. So change in potential divided by the change in distance. Now the change in potential is still 10 megajoules per kilogram, but the distance is smaller. It's only 1.8 times 10⁶, so it's changing more quickly, which gives us a stronger gravitational field strength at that point. Now, this is the average field strength between those 2 points. Obviously, as you move further away from the planet, it changes in a continuous manner. So this equation should only really be used over short ranges to get the correct gravitational field strength at that point. So returning to this question where we're trying to find the gravitational field strength at 2 times 10⁷ meters from the center, I can use this equation that I just learned to find the gravitational field strength, because this is a potential against distance graph, and change in potential over change in distance is gravitational field strength, or negative of it anyway. So that means the gradient of this graph gives us the gravitational field strength. So at 2 times 10⁷ meters, if I draw a tangent at that point, that will give me the gravitational field strength at that point. So as you can see, the gravitational field strength is getting weaker because it's getting less steep as you move away from the planet, but we're interested only at the gravitational field strength at 2 times 10⁷ meters. So if I take these 2 points and I do change in y or change in x, taking care to include the powers and everything, I get a field strength of 0.81 newtons per kilogram. That's at that point there.